Welcome again to chemical reactor theory. What we have been discussing in module 5, in module 6 is gas solid or fluid solid reactions, in which those type of reactions where solid is also participating in the reactions. In module 5, we considered cases where the solid was not participating in the reactions. So, let me generally talk about what reaction would be. Let us say we have A in the gas phase reacting with B in the solid phase. Okay. So, this B might be an ore, it might be a metal, it might be camphor, it might be coal, it can be whatever it might be biomass when it comes to biomass gasification. Okay. And the reaction will lead to a product P. Let us say the product P, or I will just call it as a fluid phase, it could be gas or liquid, plus let us say Q is in the P is in the fluid phase and Q might be in the solid phase. Okay. So, this is the situation, that general situation that we are talking about. Okay. Not all cases will involve situations like this. Okay. So, for example, if you look at sublimation or basically those types of reactions where solid is reacting with itself, it might be basically a reaction of the form Bs going to Pf. Okay. If we are talking about, let us say, camphor oxidation or burning, okay, that is going to be Af plus Bs, that will give you Pf, okay, or dissolution. Okay. Burning with ash formation, or various other cases. So, burning with ash formation, reaction with solid formation, or only one part of solid reacts. Okay. So, what I mean by B plus Q of S is, what is ash? So what's the composition of coal? So, for example, Indian coal will have something like 45%, 50% of material that can burn, and remaining 45-50% of the material that does not burn. Those are minerals that won't burn. Okay. So, Q in that case might be those things that do not burn. Okay, and those are left behind. If we talk about decoking of a catalyst or reactivation of a catalyst or a deactivation of a catalyst, you have a catalyst pellet, and most of the pellet, for example, let us say it is gamma alumina, platinum and gamma alumina that has coked, then you have platinum and alumina which won't burn, it is only going to be coke that will burn, right. So, B in that case represents the coke, Q will represents the non-burning part. Okay. So, that would be the case, the other case that would happen. Essentially, whether it is this or this, we will treat it pretty much in the same manner. Okay. And what else can we have? So, we have solid only, solid plus fluid, and we can have solid B plus S. Okay. And this would be the other cases. So, in all cases we always have a solid that is in the reacting part. Okay. If the solid is not present in the reacting part, this is not covered in module 6. That's all it means. It doesn't mean that all reactions must have solid. Okay. So we have a solid that is reacting in the model part. We may or may not have in module 6. We may or may not have a fluid that is reacting. Okay. The products that are formed could either be solid or fluid or both solid and fluid. Okay. So solid plus fluid reacting to give fluid only, solid plus fluid reacting to give solid plus fluid. Okay. Solid plus fluid reacting to give only solid is relatively rare, but yeah, you can have that also. And that would be corrosion. Okay. So far we have not talked about these cases. Okay. We have only been dealing with what happens when there is fluid that is diffusing and reacting. Okay. Now we are going to now talk about solid as well. So in this lecture we will start talking about solid as well. Okay. Now there was a question, and the question was, let us say you have a pellet, and this could be module 5 or module 6. The pellet might be catalytic, pellet might be reacting, it is a porous pellet. Okay. And so the reaction is taking place within the pellet. Okay. Now we solve this to obtain okay. In a situation like this, what should I use? Is R net, is it equal to eta or which ones do you use? First one, anything else? Second one? Now question is, are these different? Are these values different? If you do it correctly, are these values different? Okay, we are only talking about a single particle. Let us not talk about composite and all that. Let us only consider a single particle. They are all the same. How did we calculate eta? How did we calculate eta? for first order. We did this for first order, right? That's how we calculated eta. What was our thing of flux matching? The flux that is coming in, area multiplied by the flux, sorry. The flux that is coming in multiplied by the surface area is equal to the net reaction that is taking place in the pellet. Okay. I had said that you can calculate your eta either based on d dc by dz or based on the integration. I also very quickly mentioned that integration oftentimes tends to be tougher to calculate than it is to calculate d dc by dz. Okay. So, lot of times we might actually take a shortcut and calculate it by d dc by dz. What did I say the other thing to do? If it is a composite slab or if it is a slab where flux comes in, flux goes out, then dc by dz at this point minus d dc by dz at this point is going to be equal to reaction within the pellet. So, integral from 0 to L in this pellet, if flow comes in and flow goes out, will be equal to the difference between the two flows. What example did I give in the previous class? Let us say lunch thali is coming into this room and we are just transferring it from here to the next room. Okay. If we eat a gulab jamun from that, integral of gulab jamun eaten from this end to this end is the rate of reaction, which is going to be exactly matched by the thali coming in minus thali going out. Thali coming in minus thali going out is equal to 1 gulab jamun. Negative of 1 gulab jamun is what went into my tummy. Both, that subtraction is 0. You take this guy on the other side, those two are equal, right. So, yes, I have made a mistake over here. This is what it should be. Okay, sorry, not here. dV. The dV would be AdZ. Okay. So, which one can you use? Any. You can use any. When it comes to reactor design or reactor analysis or a reactor simulation, if possible we would want to use the first one. When it comes to analysis of a pellet, okay, we would either use the second or the third, whichever is more convenient to use. Okay. Why? Just because they are more convenient to use, that is all. So, use whichever one is more convenient. Okay. As a matter of fact, in research, so I think 2021, we've published a work on basically hydrogen storage. Okay. So, you have basically pellets, those were pellets of this type. You remember I mentioned that the pellets were pelletized by putting carbon inside it, and the carbon tended to organize like this. Now, because this was a reaction plus heat transfer problem, therefore we couldn't use any of the eta that were available in the literature. So, what did we do? I will come to that in the last module of this course. What we did was we had one reactor model where the concentration was changing from the bottom of the reactor to the top of the reactor, and at each location we had a pellet model. Okay. These models are called 1D or 2D plus 2D or 1D plus 1D or N 3D plus 3D models or 3D plus 1D model, because one dimension is varying along the reactor. Okay. So, Z and R it might vary. So, it might be 2D in the reactor domain, and each pellet might be a 1D model, which is a separate 1D model that is varying along the radius of the pellet. If it is 1D plus 1D, it is a little bit simpler, because then you have to consider only one equivalent pellet at each location. Okay. If it is 1D plus 2D model, okay. So, let us say this is the reactor and we are doing 2D, and let us say we have 50 zones in this direction and 10 zones in this direction. Okay. We will have one model for this reactor, okay, and 500 models for each of these pellets. Okay. For each of these pellets we will solve 0 equal to del square d del square c plus r. Okay. For each pellet, each of those 500 pellet we will solve this. Once you get the solution similar to the one that I showed in Excel, we will integrate it over the entire region. Okay. We will also calculate d dc by dz, okay, and use them. Why do we calculate both of them? We calculate both of them for error checking. Okay. These models are extremely complex, and because these are numerical methods, there would be errors in the numerical methods. Okay. So, we will do this for error checking and then use it. So, in a reactor, as much as possible we will use the first equation. If because of the special situation in the reactor we are not able to use the first equation, we will use the second equation. The third equation we will use for error checking. That is what we do in research. Okay. So, let us get back to where we are. So, I hope this aspects of it are reasonably clear to you. Okay. We use things, so yeah, then you, so do not come back and later on and ask me question that you said you can use any of them, I use this, but my answer is wrong. If you used it in an incorrect way, yeah, your answer could be wrong. For example, if you only talked about the plate coming in, forgetting the plate going out, okay, just based on d dc by dz, your answer would be wrong. If I look at this particular pellet that I am showing over here, okay, you are not passing on the plate, okay, you are just consuming whatever comes in. Okay. If you are consuming the entire plate, why does the concentration doesn't fall to 0, but you saw that case, right? In one case the concentration fell to 0, in another case concentration remained more or less at 1, and in another case concentration fell to 0.54. Remember Excel sheet approximately? Yeah. So, what happens? Plate is coming in, it is not going out. How come in one case the plate was completely empty, in another case the plate is nearly full? Any thoughts on plate analogy with your CRE? Depends on how fast or slow you are eating in relationship with how fast or slow the plate is coming in. Okay, it is not one plate coming in and one of you eat. In one case the room was only this row, in another case the room was these 2 rows, in the third case the room was all 4 rows. Okay. By the time the plate came to you, it was all empty, unfortunately. These 3 rows ended up eating all the food that was there on the plate, so the concentration fell to 0 by the time that plate came to you. Okay, but it was not one plate that was coming, continuously plates were coming in. Okay, so let us say there are 5 things on the plate. Nothing. Okay. The smallest pellet over here, oh, one more plate, one more plate gone. So by the time, so there were plates piling up with food almost uneaten and their tummy is full, right. So that is what we have done. Now that was with respect to how large the row size was or the classroom size was. Instead, if you see the change in K, what is the change in K? Slow motion eating, eating very quickly. What is the change in D? That is very fast D, otherwise slower D, right. So those are the differences. The effect of slow D is same as the effect of fast K is same as the effect of square of this room, right. L square root of K by D or L square K by D. Okay. So that is the context of what we have done in module 5B. Module 5A is more about how quickly the plates from outside can come to the window. Module 5B is how quickly you take those plates from the window. Okay. Module 6 is how quickly your tummies are getting full, and as your tummies get fuller and fuller, your rate of eating might also decrease. Okay. And as your tummies get completely full, these people will not eat anything, they will just pass on the plate. These people will eat just a little bit and pass on the plate. So initially no food is coming over here, thereafter they reduce their eating and some food just comes over here, then they stop eating because their stomachs are full and more food comes over here. That was not relevant in module 5A or B. That is relevant in module 6. That is the difference between module 5A and module 5B and 6. Is module 6 we are also interested in your tummies. Module 5A and B we were not interested in your tummies. Maybe like a Harry Potter or something, there was a black hole or whatever that thing. So food was going there, it will go away. Okay, but here your tummies are getting full. Okay, so that is the difference. Okay, all right. Any other questions? Okay, so this we did earlier. So in a general model, the fluid can diffuse into the particle and react simultaneously, and therefore we have the case of internal diffusion. The size of unreacted or the partly reacted core drops due to the reaction. So that means this row is no longer eating. That would be relevant when you have solids that are formed because of reaction. Okay, if solids are not formed because of reaction, you will only have your particle shrinking or your particle reacting uniformly. Okay, the completely reacted solid may disappear completely because the products are only fluid, there is no solid product, get replaced by product or ash. That means B is being replaced by Q, or out of B and Q only B is getting reacted. Okay, or it could be a combination of both, in the sense that there is B plus Q both being present, but B is present to a much significant extent. So as a result, the Q does not stay in shape like earlier, but the Q also shrinks. Okay, all of these are possible. We are, as I said, going to consider the three different cases. Okay, the one case that we are going to consider is shrinking particle model. Okay, that we will consider, we will assume that the particle is non-porous. Again, do we need that assumption? No. Okay, the particle could be porous, your analysis for your gas phase or the fluid phase only differs, your analysis for the solid phase remains the same. Okay. So, the shrinking particle model, you go from this size to this size. Okay. The shrinking core model, okay, or core and shell model is we have an outer shell which is of the spent material. So, outer shell contains Q and the inner core contains B. Okay. Volume reactor model is the other end of the shrinking core model, where the diffusivity is extremely fast, alternatively the particle is very small, alternatively the K is very small. Okay, they are all in relationship with each other, which basically means your phi Thiele modulus is small and therefore the entire particle is reacting uniformly. Okay. So, you can think shrinking core model as the more common situation, and the shrinking particle model, but with the reaction only taking place at the surface might be one end of the shrinking core model, where you have the core shrinking as well as your shell also shrinking. So, that is also possible. So, you can get more complex situation than this. We will not necessarily study more complex situations. Okay. So, this is something that we would consider. Okay. So, let us say we have, okay, let us do this. Okay. This is the particle, okay, not reacting because there is no longer B that is present in the outer shell. Okay. Inner core is reacting that because there is B still present over there. Okay. So, let us look at external diffusion. Oops. How do you think the external diffusion can look like? Okay. It will either be flat or it will be a straight drop. Okay. So, either of them is possible. So, when is the first case possible and when is the second case possible? Okay. Case number 1, the first one, when it is flat, that means when will that happen? There is no external diffusion resistance, which means what? Kg is very large or Kg is very small? Kg is very large, right? Your CAS was equal to for first order reaction, right? Sorry, Kg divided by K dash plus Kg, remember? Okay. If Kg is much greater than K dash, then you will get CAS approximately equal to Kg divided by Kg multiplied by CAB, so approximately equal to CAB. Okay. So, this happens or eta multiplied by k multiplied by A by B, either of those cases. Okay. If not, then you will see the fall. Okay. Okay. Let us talk about the next case. What is going to happen? Again, there is diffusion with no reaction. Okay. So, diffusion with no reaction means something like this. CaS2. Okay. Usually slope of the gas phase is going to be less steep compared to the slope of the solid, but does not have to be. Thereafter, inside the pellet. Inside the pellet, you might have the case like this, or the case like this, or the case like this. Okay. When does the first case happen? More or less very flat. You recall the Excel sheet in 5B. When was the concentration more or less flat? Either very small pellet or very small k or very large d, right. Diffusivity is very small, very large, reaction is rate limiting. That is the case when things are flat. Okay. Exactly the same as it was in the external diffusion case, okay, or in the internal diffusion case without reaction. Okay. There also, yeah, I should add those. Okay, d by L square can be large because d is large or because L is small. Okay, CaS3 approximately equal to CaS2. Phi less than 1. Let me say phi square. Okay. Phi was, I think if I remember correctly, 0.35 or something like that, 37 or something. Okay, phi square was pretty much as large as 0.115. Okay, even then we saw this to be fairly flat. Okay. All of this we are still talking about the gas phase. Now let us talk about the solid phase. Is there any solid present in the gas diffusion layer? No, there is no solid in the gas layer. Okay. Is there reacting solid in the shell? No. Okay. So we do not have to worry about solid in the gas phase, we do not have to worry about the solid in the non-reacting core, we only have to worry about the solid in non-reacting shell, we only have to worry about the solid in the reacting core. Okay. This particular case, we talked about it yesterday. If the gas phase species concentration is uniform throughout the core, the reaction rate is going to be constant throughout the core. Okay. Okay. This particular extreme, okay, is where okay. In this particular module, we will only consider the solid dissolution case. Okay, we will not consider an outer shell. Why? Just to keep things simple. Okay, can there be an outer shell or not? Depends on which situation we are in. There can be an outer shell if a solid is being formed as a result of the reaction. There won't be an outer shell if no solid is being formed because of the reaction. Okay. So really it depends. Okay. But we will take a case where solid does not form as a part of the reaction. So for case number 1, we will take a case where A plus B going to Q or A plus B going to P plus Q. For the third case, we will take the case where A plus B is going only to P, there is no Q being formed, okay, just for simplicity. Okay. And this middle case is what you see in the textbooks as shrinking core or core and shell model. Okay. That is how we will deal with these cases. Okay. The next slide is again talks about these specific approximations that I talked on in the previous slide. Summarizing previous slide. Okay. Fast diffusion in the film CAB is approximately equal to CAS. Fast diffusion in the outer shell CAS is approximately equal to CAC. Fast diffusion in the core, that is the case when phi square is much less than 1, okay, and therefore concentration within the core does not change at all. Okay. Fast reaction case is where the concentration drops immediately to 0. Okay. These are the various approximations that will allow us to simplify our analysis, and then we will do the general analysis. Okay. So, for the fluid we are going to assume a pseudo steady state. Okay. Pseudo steady state is assumed insofar as your pellet is concerned. If you are looking at reactor, think about tummies getting full. Okay, tummies are getting full because the plates are coming from outside. Okay, let us say outside there are 100 plates and they end up sending 25 plates before all of us are full. 100 goes from 100 to 75. There is a 25% conversion outside also. Okay, that will take place over a longer period of time compared to this particular process taking place. Okay, that we will cover in module number 9 and 10. Okay, we will not cover that in this module. In this module we are only interested in this room, we are not interested in the effect of this room in consumption of plates outside. Okay, so from the kitchen the plates are coming in, or kitchen the food is more food is cooked. Okay, how does the food disappear from kitchen is not something that we are modeling. We are only modeling right now what is happening in this room. Okay. Now, again summarizing the same thing that we talked about over here. Okay, diffusion in the film, diffusion in the outer shell, diffusion in the reacting core. Okay. Now, how do you, but CAC, the CA at this point and CA at this point, what we had called as CAS and CAS2, which we are calling, which in the notes I have called it as CAC. These are still unknowns. How do you obtain that? Okay. How do we obtain that? How do we obtain CAS is basically the flux that comes in over here will be exactly matched by the flux multiplied by area, flux multiplied by area going in over here. Okay. This matching will give us CAS. Okay. The flux that comes in over here will be exactly matched by the flux that goes in over there, which will exactly matched by integral of reaction that is taking place within the core. Okay. So, you can use, again it is going to be two equations in one unknown. Okay. If you have realized based on what we have discussed so far, those all three will be equal. Okay. So, you can use that. Okay. So, this flux matching is used to eliminate also known as okay, and this flux matching will be used to eliminate CAS. Okay.